Okay, so today we're going to talk about relations. This is section 8.1 in the sixth edition of the textbook. And the most direct way to express a relationship between elements of two sets is to use ordered pairs. And binary relations are relations that are made up of two related elements. So section 8.1 is going to deal with binary relations, and then later on we're going to extend that to relations of size n or n-ary relations. So let A and B be sets. A binary relation from A to B is a subset of A cross B. In other words, a relation from A to B is a set R of ordered pairs where the first comes from A and the second one comes from B. So ARB denotes that AB is a member of that relation. A with R with the cross out indicates that AB is not a member of that relation. When AB is a member of R, we say that A is related to B by R, the relation. So let A be a set of CS students, for example, Keenan, Jamie, Mike, and Joel. And B be a set of lower division CS courses. For example, 141, 150, 151, 241, 266, 321, all of your favorite courses there. And R is a relation consisting of pairs A, B, where A is enrolled in B. So in this example, Joel is enrolled in CS 151, Mike is in CS 241, Keenan is in CS 266. Those are all in R. But Jamie being in CS 150 is not in R. So Jamie's not enrolled in CS 150. So another example, we'll let A be 0, 1, 2, and B be the set AB. Our relation is 0A, 0B, 1A, and 2A. And that's the relation. So here, 0 is related to A, but 1 is not related to B. And we can view that as either a table where we have an X that indicates those two elements are related and a blank if they're not, or as a graph with a arrow directed to the element from the first set to the element that's related to in the second set. So in that graph, we could see 0 is related to A and 0 is related to B. 1 is related to A, but 1 is not related to B. Likewise, 2 is related to B, but not to A. For me, the graph is fairly natural, but, for you, it may be the table. Recall that a function from A to B assigns exactly one element of B to each element of A. The graph of F is the set of ordered pairs such that F of A is equal to B. Since it's a subset of A cross B, F is also a relation. The converse is not true, since relations are more general in functions and can express one-to-many relationships. For example, 0 is related to A and 0 is related to B in the previous example. That would be an indeterminate function. And so the relations are more general in this case. A relation can also be defined on a single set. A relation on a set A is the relation of A, the elements of A to the elements of A. So let A be the set 1, 2, 3, 4. What are the ordered pairs in the relation R is equal to A, B, where A divides B? Well, 1 divides 1, 1 divides 2, 1 divides 3, 1 divides 4. 2 divides 2, 2 divides 4, 3 divides 3, and 4 divides 4. You can also display this as a graph or a table like we did in the previous example. So consider the following set of relations on the set of integers. R1, A is related to B if A is less than B. R2, A is A is related to B if A is greater than B. R3, A is related to B if A is equal to B or A is equal to minus B. R4, AB, A is related to B if A is equal to B. R5, A is related to B if A is equal to B plus 1. And R6, A is related to B if A plus B is less than or equal to 3. Which one of these relations contain 1, 1? Well, R1, obviously, because 1 is less than or equal to 1. R2 does not, because 1 is not greater than 1. R3, A is equal to B. Obviously, 1 is equal to 1. R4, 1 is equal to 1. and R6. 1 plus 1 is less than 3. Which ones contain R2? Well, R1 and R6. Which ones contain 2, 1, R2, R5, and R6? Which ones contain 1 minus 1? Again, there you have R3 because A is equal to minus B. And which ones contain 2, 2? R1, R3, and R4, just like we did with the 1, 1, but R6 is not there because 2 plus 2 is 4, and that's not less than or equal to 3. There are two raised to the n squared relations on a set with n elements. This is because A cross A has n squared elements, and there are 2 to the n subsets of a set with n elements. A relation on a set A is called reflexive if A is a member of the relation for every element A in A. In other words, it's reflexive if each element is related to itself. So look at these relations here, R1 through R6. Which ones are reflexive? Well, in R1, we have 1, 1, 2, 2. We don't have 3, 3. R3, we have 1, 1, 2, 2, 3, 3, and 4, 4. That's good. R2, we don't have 2, 2 in there. We don't have 3, 3, and 3, 4. R5, we have 1, 1, 2, 2, 3, 3, and 4, 4. So R3 and R5 are the reflexive ones. Consider the following relations on the entire set of integers. Which ones of these are reflexive? Well, the ones where you have the equality are going to be reflexive. And so in general, if you have the equality, they're going to be reflexive. So those are R1, because that's less than or equal to, R3 equality, and R4 equality. A relation is called symmetric if BA is a member of R whenever AB is a member of R. And a relation R on a set A such that for all AB in A, AB is a member of R and BA is a member of R implies that A is equal to B is called antisymmetric. And note that symmetric and antisymmetric are not opposite terms here. So which one of these relations are symmetric? Well, if we have 1, 2, then we have to have 2, 1. If we have 3, 4, then we'd have to have 4, 3 in R1. So that one's not symmetric. R2, that one is going to be symmetric because we have 1, 2, and 2, 1. R3, we have 1, 2, 2, 1. We have 4, 1, and 1, 4. So that one is symmetric. The others are not. Definitely R6 is not symmetric. R4 ends up being antisymmetric since there's no pair AB such that BA belongs to the relation. So that one is quite interesting that it's antisymmetric. And R5 is only symmetric when A is equal to B, so it ends up being antisymmetric. R6 is antisymmetric for the same reason that R4 is. For the general integers, which one of these are symmetric? Well, it turns out R1 is not going to be, since A is less than or equal to B, means that B is probably, if A is 3 and B is 4, then 4, 3 is not going to be in there. R3, because of the equality, that's going to be symmetric. R4 the same with the equality, and R6 is also symmetric. R1 is antisymmetric since A is less than or equal to B and B is less than or equal to A implies that A is equal to B. R2 is antisymmetric since there are no elements such that A is less than B and B is less than A. R4 is also antisymmetric because if A and B are related, that means that they are going to be equal. just by the definition of that one. R5 is antisymmetric since there are no elements such that A is equal to B plus 1 and B is equal to A plus 1. A relation R on the set A is called transitive. If AB is a member of R and BC is a member of R, then AC is also a member of R for all A, B, and C are part of A. So which ones of these are transitive? Well, these ones take a little bit more work. So here we have 1, 2, 2, 1, and 1, 1 is related under R1. 3, 4, and 4, 4 goes back to 3, 4, and 4, 1, but we don't have, and then 4, 1, and then 1, 2, but we don't have 4 related to 2. So R1 is out. R2 is also going to be out. R4 and R5 will be transitive, and R6, there's not enough there. But because it only has one element, that means that it's oddly enough transitive by definition. Consider the following set of integers, and here we're going to see which ones are transitive. The ones that are transitive, if A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. R2, the same reason. R3, because of the equality, and same for R4. And R5 can be shown to be not transitive with A is equal to 2, B is equal to 1, C is equal to 0. Is divides reflexive, symmetric, and transitive on the positive integers? Well, let's take a look. Is it reflexive? Yeah, definitely A divides A. It always divides itself. Is it symmetric? If A divides B, does B divide A? That's probably not the case, but it is transitive. So it's not symmetric because A divides B doesn't mean that B divides A. In fact, generally not unless they're equal. And you can combine relations using the set operations, union, intersection, set difference, and symmetric difference. And symmetric difference was the set of elements contained in either A or B, but not in both A and B. And so you probably recall that from CS141. If not, we'll go back and review it when we do the lecture a little bit of detail. And again, we can combine those relations in the same way that we can combine sets, because they're really just sets of ordered pairs there. And the same with more general ones. We can do those, set differences, symmetric differences, intersections, unions, etc. We can also do composites. And the composite of two relations is the relation consisting of the ordered pairs where A is a member of A and C is a member of C. And we denote that by using a little hollow bullet point between S and R. So what is the composite of the relations R and S, where R is the relation 1, 2, 3 to 1, 2, 3, 4, with R is 1, 1, 1, 4, 2, 3, 3, 1, and 3, 4. S is the relation from 1, 2, 3, 4 to 0, 1, 2, with S is 1, 0, 2, 0, 3, 1, and 3, 2, and 4, 1. Well, we look at all the ordered pairs in R and S where the second element of a pair in R agrees with the first element of a pair in S. So again, the second element in R agrees with a pair that's in S. So 1 agrees with 1 in the first two. So 2, 3 in R would agree with 3, 1. So that would produce 2, 1 in SR. So we would get the 1, 0, which is the one I pointed out. The example pointed out in the book was the 2, 3, and 3, 1, which will give you 2, 1. The same with 1, 1, 2, 2, 3, 0, and 3, 1. And you can also do powers by basically doing those composites repeatedly on the sets. And so we can do those composites. So next time we'll talk about in-area relations, and we'll have a little bit of stuff about their uses in databases. So we'll find an application in computer science. Hey, thanks so much for tuning in and watching. Appreciate it.